Hey everyone, this is Mr. Weissert. We're going to be doing yet another probability lesson in AP Statistics. This will be Module 2, Lesson 4 in my notes, page 156. You'll find this in AP Classroom, topics 4.7 and 4.8, and in section 6.1 of this textbook, The Practice of Statistics, updated 6th edition. We're going to be talking about sample spaces, random variables, probability distribution, and particularly discrete random variables. Think about flipping 3 coins. In this case, you're going to have 8 options. Heads, 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 tails, heads, tails, heads, tails, heads, 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 tails, 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 heads, tails, 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 heads, and 3 tails. Now, if we define X as the number of heads obtained in 3 tosses, we can actually make a distribution table out of it. What you'll see is the number of heads, either 0, 1, 2, or 3, and the likelihood of that happening. So with no heads, 1 out of 8, well, that would be 3 tails. With 3 heads, that would be 1 out of 8 as well. And then some combination of heads and tails between them, so you can get 3 8s and 3 8s. Now, the numbers 0, 1, and 2, 3 are discrete values. There are no caps, so we call this a discrete random variable. And like any probability distribution, your probability should add to 1. Let's look at a scenario. How many children are in your family? Let's say I made up some numbers. You know, if I polled a class of 20 people and I said, hey, how many kids do you have in your family, including yourself? You might see a breakdown like this, 3, 9, 4, 2, 1, 1. And we could get probabilities from that. So if I look at all these numbers here, if I polled 20 people, well, 3 out of 20 have 1, 9 out of 20 have 2, and so on. Now, why is this a probability distribution? Why is it valid? Well, all of your probabilities are between 0 and 1, and they add to 1. Can 5.7167 be a possible value for X? No, you can't have a fraction of a child in your family, so it's either going to be whole numbers, and that's why it's a discrete number. You may be asked to make a histogram. Now, you can use technology to help you. With something like this, it's best to take your probabilities and get decimals for it. So 3 divided by 20 is 0.15, 9 divided by 20 is 0.45, and so on. That allows you to make your histogram a little bit easier. So now you can take your bars along 1, 2, 3 through 6 and estimate what the height is and draw it. Make sure that you put an x-axis, children and family, probability. So it might look something like this. And you may be asked to describe the shape of that histogram. And if you look at the shape, it looks like it's going to be a little bit skewed to the right, and it's got a peak of around 2. So you've done these before, so that shouldn't be new. Now, we may be asked to calculate some probabilities using the table. And so if you look at the first one here, it's going to be describe in words what the probability of X is greater than or equal to 3, X being the number of children in the family, and then find it. So first, if a student is randomly selected from the class, the probability that they will be part of a family with 3 or more children is, and then from there, well, you'd want to calculate that. So if you look at the probabilities, they're all down here, and whatever those add to will be your answer. So in this case here, it's going to give you whatever those add to, which is going to be 0.40. Part C is basically doing the same thing. It says find the probability what Px is greater than 3. So the only difference is it doesn't have the equal to. But it's the same scenario. If a student is randomly selected from the class, the probability that they will be part of a family with more than 3 children. And that's going to incorporate just the probabilities that you see here circled, 0.1, 0.05, and 0.05. And those are going to add to 20% or 0.2. And that's about all there is to that. You may be asked to get the median of the number of families. So you could list out all of your numbers. For instance, I have 1 3 times. I got 2 9 times. And I got 3 4 times. And I'm not going to list them all because you already know that the median is the middle number at this point. So the middle number would be, since there are 20 numbers, somewhere between the 10th and 11th number. So if I just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I know that my median should be 2 because the 10th and 11th number are both 2. So the mean, well, that's going to require a little bit of adding together and dividing by 20. So you know that the mean is simply taking all your numbers and adding them. So you'd want to list them out. and then take that number and divide by 20. Whatever that adds to, divided by 20 should get you what the mean is. And you'll notice that the mean is 2.6 children in this case. Remember, we used the little X with the bar on top of it to write the notation. And that mean in this problem simply is the average of the number of children in this sample of 20. It's also greater than the median. Why is that? Well, the data is skewed to the right. So since the data is skewed to the right, you're going to find that that mean is generally bigger than the median. You can also calculate the mean and the median from your calculator. So if you go into your stat menu, you can either enter all the numbers in, and just account for the frequencies there. And your mean is going to be 2.6 as the top number. You're going to be asked for the standard deviation later in this lesson, so I'll just kind of remind you where that is. It's not the S of X that we're going to use for these. In probabilities, we actually use the sigma X, the lowercase sigma right there that has that little Greek symbol. And that is the parameter for standard deviation. You'll see it over here too. Now I want to focus on this this one in the right here, because this is how you're going to be doing it for most of our stuff. I wanted to model that with you guys. So if you're in your calculator, your TI-84, you can go to your stat menu, and that's going to be right here in the middle, and just go to edit, and you'll type in your 6 numbers. And then over in L2, we actually put our probabilities, not our counts, our actual probabilities. So 0.15, 0.45, 0.2, 0.1, 0.05, 0.05, and 0.05. Now, when you're doing your calculations here, a couple things. First, you want to make sure you go to stat calc. It's still one variable, but that L2 is where your frequency goes. So if you hit second 2, that'll pull up a frequency list. And what that'll do is that'll give you your mean like before, but it only gives you the standard deviation in the sigma form, which is what we're going to be looking for anyway. It's just a parameter. And you can actually scroll down and get that median. Remember, we said the median was 2, so we can still verify that it's 2 here, as well as the other numbers in your 5-number summary. Now remember, standard deviation is a tricky formula. So generally we let the calculators do the work for that. So if you're asked to find the standard deviation and not show your work on it, like this case here, and we're asked to interpret it, we'll get the technology piece done, and then we can get that number and find it. So remember, we got a standard deviation of about 1.28. And we're going to use that number to make an interpretation. So 1.28 is your standard deviation. And so the interpretation is going to be, if we randomly selected many students from the class, the typical number of children in their families would vary by about 1.28 children from the mean of 2.6. You don't really need to say what the mean is since we already calculated it, but standard deviation is the typical distance from the mean. So we want to write that in context of this problem. The mean is also called the expected value in a discrete random variable. So with an expected value, it's what we would on average expect the value to be. And it's not going to always be it's rarely ever going to be a whole number. Most of the time it's going to be a decimal. And we're going to use whatever we get here when we calculate that. It's kind of a difficult formula. On your formula sheet, it's going to look like this. On your AP Stats formula sheet, you're going to see this little uppercase summation with this little xi and pxi. And all it really means is we're going to take all of our individual values in our distribution and simply multiply them by the probabilities. Keep doing those and add them all together. And whatever that ends up being, that's going to be your expected value or mean in this case. So let's look at how to get that. I'm going to actually go back and show you how to do that in the previous problem. If you remember in our problem with the number of children in the family, the mean was 2.6. Now, if I'm using the expected value formula, I'm simply going to take all of my values here, my discrete values, and multiply them by the probabilities down below. So I do 1 times 0.15, plus 2 times 0.45, plus 3 times 0.2, and so on. And when I do that calculation, I will end up getting the 2.6 from my mean like I got before. It's actually a pretty simple formula, straightforward to use. It's a lot quicker than adding up all your numbers and dividing by how many there are. So I generally try to stick with this when I'm doing expected value. All right, let's look at another example. This one has many parts. In 1952, Dr. Virginia Apgar suggested 5 criteria for measuring a baby's health at birth: skin color, heart rate, muscle tone, breathing, and response when stimulated. She developed a 0-1-2 scale to rate a newborn on each of the 5 criteria. A baby's Apgar score is the sum of the ratings on each of the 5 scales, which gives a whole number value from 0 to 10. Apgar scores are still used today to evaluate the health of newborns. Although this procedure was later named for Dr. Apgar, the acronym APGAR also represents the 5 scales: appearance, pulse, grimace, activity, and respiration. Which APGAR scores are typical? To find out, researchers recorded the APGAR scores of over 2 million newborn babies in a single year. Imagine selecting a newborn baby at random. That's our random process. Define the random variable x equals APGAR score of a randomly selected newborn baby. The table gives the probability distribution of x. A, write the event the baby has an APGAR score of 0 in terms of x, then find its probability. Well, since x is the name of our variable, we would say p x equals 0, and then we would do 1 minus all of the other numbers added. Notice I didn't write them all out, because there's 10 other numbers there, and that's too long to write. So use the ... abbreviation, between maybe your second and last number. Save yourself a little bit of room. You do have to show work, but be smart about it. So you're adding up all these numbers first, because everything should add to 1 in a probability distribution. When you subtract that from 1, you get 1 minus 0.999. And that's going to give you a very small probability, 0.001, 1/10%. Part B, doctors decided that APGAR scores of 7 or higher indicate a healthy baby. What's the probability that a randomly selected newborn is considered healthy? Well, 7 or higher would be the 4 numbers starting at 7. Adding those together, you're going to get 0.908. Now look at how I wrote it. I'm writing it in the correct notation. So when I'm writing an expected value, I do P, and then I use the letter that the expected value is named. So in this case, it's X, and just follow the directions. So this one says 7 or higher, so greater than or equal to 7. This one says equal to 0, so write equals 0. Part C, calculate and interpret the expected value of X. Well, we needed the probability for 0 to be able to do that. Now, the expected value formula is, well, you can do this and go into your calculator and type all that in. I would actually do that first before I started writing stuff in the formula, because I want to be able to get a number, so that way I can check my work. So I would list all my numbers, 0 to 10, list my probabilities in L2. Remember to put L2 in your frequency list. Don't forget that. And then get your calculations using your one variable stats. And you're going to get a mean of 8.128. And remember, the mean is the expected value. So we write our little notation, E of X, which is equal to mu of X. And then you write a couple iterations of your formula. I'm not writing all 11 of these. So I'm going to do 0 times 0.001 plus 1 times 0.006. And I'm going to put a plus ... and skip over all this stuff, and then go at the very end, plus 10 times 0.053. I'm going to use my calculator's value to get that. So my expected value is X with the bar on top. So it's going to be 8.128. And then the interpretation is, if many, many newborns are randomly selected, their average APGAR score will be about 8.128. Part D is just talking about how would you describe the shape of the histogram. So if you look at that histogram, it's definitely going to be skewed toward the left. It's single peaked, and 8 is the peak. So I'm going to actually wrote 8 on there. It's actually at 9. So I'm going to change that to 9 real quick. There, now we have that fixed. So it's going to be single peaked at 9 and skewed to the left. Now let's review how to get standard deviation because we'll have to show work for that in some situations. So on your AP formula sheet, you're going to have this formula down here. And it's kind of tricky, so it's better to just kind of explain how to work that out as we go, but it's always going to have a square root in it. And you're going to have that little sum where you're adding a bunch of things together. So let's kind of walk through how to do that using this problem. Verify that the standard deviation is 1.437 and interpret the standard deviation. Well, first I am going to go to my calculator and I'm going to do my one variable stats and put L2 in my frequency list for my probabilities. And I'm going to make sure that my standard deviation is what it says. So it's going to be 1.437. But when you're showing that work, let's follow the formula. So what we're going to do is we're gonna look at the formula that's provided to us. It's got the sum. It'll have each individual x value minus the mean. We're going to square that, multiply by the probability, and we're going to keep adding those. So if you look at how I wrote it down, that first zero is going to be right here, and that's going to come from the table here. So that's going to be right there in the formula. The 8.128, that's your mean. That's what we already calculated. Close it up, hit the square button, and then multiply it by the probability for that individual value. We do the same thing with all the other numbers. So 1 minus the mean squared times its probability plus, and I'm not going to write out all 11 of these, so I'm going to skip to the end, 10 minus the mean squared times 0.053. We already know what the number is as far as showing the work. Just show that you know how to use the formula. You don't actually have to use your calculator to do all 11 of those. That's going to give you 1.437, and then we're going to be asked to interpret it. So for standard deviation, remember it is the typical distance from the mean. In a problem with probability, would say if many, in this case, newborns are randomly selected, their APGAR scores will typically vary by about 1.437 from the mean. Let's make a histogram of this. Actually, this is a different problem, so let's start to the next problem. Example 3, Pete's Jeep Tours offers a popular day trip in a tourist area. There must be at least 2 passengers for the trip to run, and the vehicle will hold up to 6 passengers. Pete charges $150 per passenger. Let C equal the total amount of money that Pete collects on a randomly selected trip. The probability distribution of C is given in the table. And you'll see we have all these individual values. So $300, $450, $600, $750, and $900. And with the probability distribution as listed. We want to make a histogram of this and describe its shape. So in this case here, we already have the scale for it. We might draw something like that. And you can see it's pretty symmetric. There might be a little bit more here than there, but I'm not going to say skewed in this case. I'm going to say the probability distribution of the money for Pete's Jeep Tours is single peaked at $600 and fairly symmetric or roughly symmetric. Let's calculate, interpret the expected value of C. Remember, in this case here, all we're doing is taking our individual values and multiplying by its probability and adding together. You can do your one variable stats and make sure that you can get your mean in there. And remember, your mean in this case is the X bar from your calculator. So we want our number to be 562.5. So our expected value will be E of C in this case, because C is our random variable. And we're going to take 300 times 0.15 plus 450 times 0.25. And you could use the dots in here if you want. I didn't because there's only 5 numbers. But you should get $562.50. To interpret that, if we randomly select many Jeep tours, Pete's going to collect about $562.50 on average. Part C, what's the median? In the case of the median, you want to look at where the 50th percentile for probability lands. So I think of cumulative probabilities. After this first number, that's 15%. And then if I go to the 450 and I add that 25% on to 15%, I'm at 40%. So I know that above 40 and below 75 would be somewhere in the 50th percent. So it's going to be right at the 600. And we would say 600 is the median. It's where the 50th percentile of the data lies. As far as calculating interpreting the standard deviation, I'm going to go to my calculator and get that first. Our standard deviation is down here. It's the 163.46. So our interpretation is going to be the typical distance away from the mean. You have to show work on calculating it. So go to our formula, and we're going to take each value, subtract the mean. So 300 minus 562.5, we're going to square that, multiply it by its probability. And we're going to do that with all the other ones, and we're going to add between them. And I'm skipping a few numbers here in the middle to go straight to the end. So 900 minus the mean squared times 0.05. And that will get me $163.46. Notice that I'm using the dollar and cent symbol because we're talking about money. The interpretation would be if I were to do many, many Jeep tours, the amount of money Pete collects varies by about $163.46 from the mean. All right, we have a check your understanding. There's, I think, a few parts on this one here. So take a look at part A. High school students in Michigan sometimes get snow days in the winter when the roads are so bad that school is canceled for the day. Define the random variable S equals the number of snow days at a certain high school in Michigan for a randomly selected school year. The table gives the probability distribution of S. So typically, the number of snow days that the students get in Michigan is 0, which I'm pretty sure that's not true. I think these are made up. But about 33% get 0. About 19% get 1 snow day. And you can see it tapers off toward the end. So it's going to be right skewed. As far as making your histogram, I would go in and first go to your L1 and L2 and enter that data in. And we can go ahead and get our one variable stats, making sure we use L2 in our list. I'm actually going to model this on my calculator for me. So if you have your TI-84 calculator out or you have the web version of it, so go ahead and enter these into L1 and L2 into your TI-84. Go to Stat, Calc, one variable stats, and make sure that your frequency list says L2, second 2. And we'll go down to calculate. Now you'll see the same numbers that I get, and you might want to jot those down because we'll need our mean and our standard deviation. But this asks you for a histogram. So as far as getting your histogram goes, you can go to your second y equals, and you can turn on your stat plot. And you press enter and turn on your plot. Now go down here, and the histogram is going to be this middle one right here, well, the third one. And make sure that your frequency list does say L2. So L1 and L2 are required to be able to do a probability distribution here. Now, I'm not going to do a zoom 9 because if I do a zoom 9, it's kind of useless here. So I'm going to go to my window and I'm going to manually set this. So if I look at my X values, they're between 0 and 10, but I want my histogram to fall right on the 0, the 1, the 2, the 3, the 4, and so on. So what I'm going to do is I'm going to make my X minimum, I'm going to say negative 1.5. I'm going to have a little bit of wiggle room on the left side. And then my X max, I'm going to say, I'm going to go one more and then do a 0.5, 11.5. I'm going to make my scale go by 1. So that when I do it like that, that means the middle of the bar should line up right on the number. The Y is dealing with your probabilities. So what's your highest probability here? Well, it looks like it's 0.33. So I'm going to have my Y min be a little bit below 0 so I can have some gap below it. So I would say like negative, maybe 0.05. And then my Y max would be, let's say 0.4. And that'll cover everything from 0 to 33%. And I'm going to make my Y scale count by 5%, so 0.05. So if I did all that, then I could hit graph, and I should get a histogram, and you can kind of ignore the axes here. You do a little view here and make that bigger. And there's your histogram. And if you hit the trace button, this bar here is 0. It's between negative 0.5 and positive 0.5. That's 33%. And you can scroll to the right and get all your percentages that way. So that's how I would do it using the TI-84. There are other applets you can use like Staplet and other websites to get it as well. So just to recap here, turn your plot on, frequency list must say L2, set your window to something like I did so you can kind of see a little bit below and above the probabilities and left and right of the X values. Make sure when you're writing your histogram, you write probability on the left side and whatever the X value is, in this case, number of snow days. So we're asked to draw a sketch and describe the shape. Well, it's going to be skewed to the right with a single peak at 0 days. All right, part B, calculate the mean of S, interpret this parameter. Well, we've already calculated with our TI-84, it's 2.17. So as far as the calculation goes, we want to show a couple steps. So again, I'm going to do 0 times 0.33 plus 1 times 0.19, and just do a plus ... and go right to the last one, plus 10 times 0.01, and you can just show that it equals 2.17. Interpretation is the average. So in many school years, if they're randomly selected, the average number of snow days will be about 2.17 days. The median is the middle number. It's helpful to have cumulative probabilities. Notice I really could stop at the 52 because the median is going to be at the 50th percentile. So 0 is too small, but the 50th number will be, or 50th percentile would be at the 1. So you could say something like the median is 1 day. It's the smallest value for which the cumulative probability is at least 50%. And your calculator will verify that that median is 1 if you scroll down here when you do your one variable stats. Compare the mean and the median. Well, in this case here, the mean is more than the median. Explain why this relationship makes sense. Well, it was a right skew distribution, so we would expect the mean to be in the direction of where the skewness and the outliers are. So it's going to be bigger than the median. Letter E, calculate the standard deviation of S, interpret this parameter. Again, we've calculated it already. It's about 2.4085. So let's write a couple steps here. We're going to write the standard deviation formula, put a square root, and just start taking your values and subtracting your mean, squaring it, multiplying it by each probability, and adding them together. Do a couple of them, put a ... end it with the last one, and then you can simply say your standard deviation is whatever your calculator says. Interpreting it, if we took many randomly selected school years, the number of snow days will typically vary by about 2.409 days from the mean. All right, let's go ahead and summarize this. A discrete random variable is a countable set of possible numbers with gaps between them. All the numbers should add to, the probability should add to 1 and be between 0 and 1. And we're going to be asked to describe the shape of the probability distribution using a histogram, which is usually the preferred way to do it, preferred graph to use it. Expected value is the mean. So it's the mean of a probability distribution. It is literally the value times the probability plus the value times the probability and so on. We're going to ask to interpret it. So if we take many random samples of whatever we're taking a sample of, the average in whatever context we're talking about will be about whatever the mean is. Always use context in that problem. Finally, the standard deviation. If we take many random samples of this thing, the value will typically vary from the mean by about whatever your standard deviation is. And you have that formula over here, the square root of the sum of each of the values minus the mean squared times their individual probabilities. And I just have to reiterate, show a couple steps when you're doing your work, but go to your calculator and get those values because there's going to be a lot of numbers to do, and we're going to be more focused on interpreting them, not number crunching. So let your calculator do the number crunching. Y'all, thanks for watching. Hope you have a wonderful day.